Did I miss anyone? They. So I'm not going to discuss the answers to the test yet because some people are still taking it. No, those who were not able to have the internet connection and those who were supposed to take other tries. No, but looking at the results, no, I think a lot about 1/3 of all students got 95 and above. No? And then so few did not make it. No, I think there's about 5 who did not make it. So if you're in the list, no, I'm going to prepare a special exam. If you haven't finished the third tries, I will allow you to take the third try until tomorrow. Okay, until tomorrow morning. By the way, no, who was it? Okay. Let me just edit this so you can view your scores. Okay. So for today, I'm going to introduce a new lesson. You can get your review options. So while the quiz is still open, yeah, you can get your marks. It's okay now. You can get your marks after the quiz is closed. Yes, it's okay now, no? Okay. After you make it, you've done an attempt. No, after you've done an attempt, submitted an attempt, you will get your marks. And then after the quiz is closed, you can also get your marks. Okay. Anyway, about 5 people did not make it, so you can still try. You can email me. No? There's a password for those who haven't uh, finished the third try. Otherwise, I will give you a special exam. It will be a harder exam. No? Special exams will be harder exams. No? Before the second formative test, because we will have our second formative test sometime or sometime by the end of the month, no, by the end of September. Okay, do you follow? Any questions so far? So okay, oh yeah, this formative test number 2, and then we'll have okay. So the second part after the first assessment is about number systems and Boolean algebra. Okay. Uh, Basically, this is binary number systems, no? And then after that, this is an introduction to hardware, no? Because most computer hardware nowadays are using binary numbers. Okay. Remember that the last non-binary computer is ENIAC during the 1940s, no? After 1945, all computers are already binary computers, which means that they're all using binary numbers. Okay, so that's why we need to discuss these topics because they will be used later now when we discuss the structure of different computer components like the CPU, the ALU, no? Even memory and so on and so forth. Okay, so this will be useful, no? So I'd like you to take a look at the crash courses. Now these are video sources from the internet which will help you understand, no? Numeric representation. Okay. At the same time, there will be slides which I have prepared, and you will have exercises which we will do later. No? So a big part of our second formative assessment will be a lot of math, no? Okay, problem solving, no? And then the third formative test will be there will be about 3 formative tests before the actual summative test. Okay, do you follow? No? Okay, so the second formative test will be about numeric representation, number systems, and then the third will be about Boolean algebra and computer hardware. No, so we must change this. No, we must add this. This is about this is not Boolean algebra but Boolean arithmetic, binary arithmetic. because Boolean algebra and logic gates will be in the third, the third session, the third part of our syllabus. Any questions so far? Okay, can we start with a new topic now? No, it's about number systems. You can download the slide. No, number systems and converting positive numbers to binary. Okay, so it's important. Binary systems or binary numbers are important because all computers nowadays use binary numbers to do all necessary computations. Okay, so lahat ng mga computations are done using binary numbers. Okay? Anyway, it's there, no? You can download the slide, and then I have an offline copy anyway. No? I have two, okay. Do you have any latecomers? Do you have any latecomers yet? It's at me if somebody's not able to, Anyway, I have I have a list here. Okay. Number systems. People will always use number systems, no? Every day we count you count, no? You count your change, you count when you go to the grocery, or do you still go to the grocery, or do you still go to the malls, no? Or even if you buy something online, okay, you always have to count how much and how much your change will be, diba? So number systems are very important to us, regardless whether online or offline. Okay. So a number system is a method of representing counts, or quantities using symbols. Okay. In the ancient times, no, the ancient farmers used to count their animals or their sheep, no, their animals using other symbols like rope ties and markings on the wall. Diba? One mark is one sheep. Sometimes they use rope ties, no? Because when they have one sheep, they will associate one tie to one sheep. When one sheep is lost, they will untie. Okay, do you follow? And then later the abacus is used to represent symbols or quantities or counts. No? So in a number system, a symbol is used to represent quantities or a count, how much. Okay, single symbols can represent limited quantities. So for example, if you have the decimal system, you can only count using one symbol up to 9, from 0 to 9. And then when larger quantities need to be represented, you need to have a combination of multiple symbols. No? Okay. Now, when multiple symbols are used, you use a system called place values. No? What is a place value? When you have multiple symbols, each location in a set of multiple symbols is assigned a weight. No? It's called a place value. Okay. The position, the farther the position is, means larger quantities, larger counts. So weight ito. Okay, any questions? So for example, in the decimal number system, the number 16 has the following place values. The number 6 has a place value of 1 or 10 to the 0 because this is decimal. When you say the decimal number system, the base for each place value is 10. Okay. Number 6 has a place value of 10 to the 0 or ones. Anything raised to the 0 is 1. Okay. Symbol, no, I'm sorry, there's a wrong spelling there. The symbol 1 has a place value of tens or 10 to the 1. Okay, so it's like weights, no? The weight of the value 6 is 1. The weight of the value 1 is 10. Now, place values are weights assigned to the positions of a number, no? So the equal quantity can be represented as follows, no? 1 is equal to 1 times 10, and 6 is 6 times 1. So we have 10 plus 6, we have the total quantity being represented is 16 base 10. Okay. The place values, no, they are weights assigned. So the first place value is 10 to the 0. The second place value is 10 to the 1, going to the left, no? And the third place value is 10 squared, okay, or that's 100, no? And then 10 cubed, that's 1000. 10 to the fourth, that's 10,000, and so on and so forth. Okay. So different number systems have different sets of symbols. For example, for the decimal system, we only have 0 to 9. Okay, and the base is 10, which means the place values come in incrementing exponents of 10. In binary, we only have symbols 0 and 1, and the base is 2, okay, which means that the place values come in incrementing exponents of 2. No? Any questions? Exponents, no? 2 to the 0, 2 to the 1, 2 to 2 squared. In the hexadecimal system, we have the value 0 to f, and the base is 16. Okay, how do we count there? It's like the decimal system, 0, 1, 2, 3, 4 until 9. But in the decimal system, 10 is represented as 1, 0. In the hexadecimal system, 10 is represented as A, 11 as B, 12 as C, and therefore F represents 15. Okay. Now you may ask, what's the use of the hexadecimal system? Now, it's like a translation, no? You follow? If you are talking to a Frenchman and a Spanish, and you're English, okay? Hexadecimal is English. And then, because you can convert binary to hexadecimal and hexadecimal to decimal. Do you follow? It's easier to convert between binary to decimal using hexadecimal than directly. Do you follow? No? Because a group of 4 binary symbols equals 1 hexadecimal symbol. There's a direct equivalent. No? But there's no direct equivalent between binary and decimal except the place values, which are different. Any questions so far? No? So place values are ascending powers of the base, starting with the exponent 0. For example, if in base 10, the first place value is 10 to the 0, the second is 10 to the 1. Okay. Third being 10 squared, fourth being 10 cubed. Okay. So for base 2, the first place value is 2 to the 0. It's still a 1, right? And then 2 to the 1, it's still a 2. And 2 squared is 4. Okay. So now you have to familiarize yourselves with the binary series. I'm sure you're familiar with the decimal series, right? 1, 10, 100, 1000, 1, 10, 100, 1000, 10,000, 100,000, 1 million, right? That's the series. For the binary series, you have 1, 2, 4, 8, 16, 32, 64. 1, 2, 8, 2, 5, 6, 5, 12, 1, 0, 2, 4. You have to memorize that because when you buy memory, you'll be asked, how many gig do you want? You want 2 gig. After 2 gig, you will have 4 gig. After 4 gig, you will have 8 gig. So it's like the binary series. Okay, buy memory for your computer. Memory comes in sizes of the binary series. Okay, any questions so far? So nobody's coming in. I think we're almost complete now, because some people are, I think one is under vaccination, one is on quarantine. You follow? So yeah, unfortunate. Now, sometimes computers need to represent letters also. More often, no? Not just sometimes, no? Oftentimes, no? Computers need to represent letters. How are letters represented? Using codes. So the common codes. Now, this IBM 701, remember, uses BCD. The early computers use BCD. And the later IBMs, the 709, the 704, use IBCD, or Extended Binary Coded Interchange Code. Now, the problem with BCD is it has limited characters that it can represent. It can only represent the numbers actually. So IBCD is an extension of the BCD adopted in the early IBM computers. But nowadays, even IBM computers use ASCII, American Standard Code for Information Interchange. Are you aware of this? No? All the characters that you found in your that you can find in your keyboard, okay, actually belong to the ASCII table of characters. No? So let's look at that. No? So you can Google the, no? I think we have it here. No? This is the complete list of, there are 255 characters. So 0 to 90, and then we have more. We should have more, no? This shows the letters, only the letters, no? But there are 256 characters in the ASCII table. For example, the small letter A is coded as 97, big letter A is coded as 65, and now they have their equivalent binary codes. You follow? So on and so forth. All the other special characters can also be found in the ASCII table. Can we have another? Here's a longer list, from 0 to 95, which are mostly letters, and then you have the extended from 128 to 223. There should be more, because 255. I'm sorry, So all the characters that you find in your keyboard, in your notepad, in your word processor, all belong to the ASCII list of characters. Do we have French, or do we have Greek letters here? Some Greek letters can be represented, I think, Kasi merong phi. There's phi. This is sigma. I'm sorry. This is, I think, phi. This is capital sigma, summation. This is phi or phi. So there are Greek letters that are represented in the ASCII table. Do we have alpha? Yes, we have alpha. We have beta. Okay. Do you follow? Ano yung gamma? Is there a gamma? Is this a gamma? So this is phi, but we use this in this is used to represent multiplication and also pi in math. And then epsilon. We have epsilon, okay? Any questions so far? So this is the ASCII table, okay? Which are actually binary codes, okay? So that computers can represent other characters other than numbers, okay? Now, let's look about binary number representation. In any numeric representation, we use to represent large quantities using limited computer memory space. Do you follow? Like, for example, the first early computers only have 4096, 4K of memory. Nowadays, they can be very large, but they're still limited. So the unit, the smallest unit of representation in a binary numeric system is called a bit. It's in short for binary digit, bit. Okay? It's the smallest element of information used by a computer. Okay? A bit holds one of the two values, 0 or 1, or sometimes we call it true or false or true. You follow? 0 or 1, on or off. Off ang 0, and then 1 is on. Okay. A set of 4 bits is called a nibble. Okay. Nibble. A set of 4 bits placed side by side. This gives a maximum of 16 possible different values. Okay. Why is that? 0 to 15. When you have 4 bits, you can have 0 to 15. Okay. Now, there are terminologies which we need to remember. The least significant bit and the most significant bit. Okay. Now, among people, when you say least significant, it means you're not important. Okay. But in numbers, now, when you say least significant, doesn't mean you're not important. Okay. It just means you have a smaller value. Okay. Any questions so far?
None po, sir.
The least significant bit. The least significant bit is on the rightmost bit. Okay. And the most significant bit is the left, drawn to the left. Okay, drawn to the left. The least significant bit is drawn to the extreme right. The most significant bit is drawn to the extreme left. And it is the bit with the greatest place value. So the significance of a bit is determined by its place value. Okay? Do you follow? No? So it has nothing to do with importance. No? It's just a place value. Okay? So if you have a nibble like this, you have 4 symbols. The first symbol is 0. The second is designated as 1, 2, and 3. Okay. The first symbol has a place value of 1. The second has a place value of 2. The third is a place value of 4. And the fourth having a place value of 8. So take note that this is an ascending exponent of 2's. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. We follow? So these are also the weights or the place values given to each position in a nibble. Okay? So for example, you have the binary value 1011. How much is it? You'll have to count. The most significant bit is the bit with a place value of 8. The least significant bit is the bit with a place value of 1. Okay? Bit 3, this is bit 3, is set. When we say set, it's 1. Okay? So it has a decimal place value of 8. Bit 2 is not set. When we say not set, it's 0. So it has no value at all because it's 0. So the first value is 8. Bit 1 is set. So it has a decimal place value or weight of 2. So 8 plus 2 na tayo yan. 8 plus 2 is 10. Bit 0 is set. So it has a decimal weight value of 1. Okay, so therefore, 1011 means 8 plus 2 plus 1. So 1011 is actually 11 in decimal. Okay. Any questions so far? So that's how we count, no? In binary. First we count, the first count is 0. The next count is 1. After 1, what will be the next count? 1, 0. 1, 0 is actually equivalent to 2 because we had one group of 2's and 0 groups of 1's. Okay. After 1, 0, what's the next count? 1, 1. It's actually 3. 3. Why 3? Because we have one group of 2's and one group of 1's. Okay. That's 1, 1. What's the next count? After 3, it's 4. The number is 1, 0, 0. Do you follow? So it's just like the binary numbers, rather the decimal numbers, but we have a smaller odometer. Okay. If you go to gas station, you have an odometer. No, where you have 0 to 9. Now in the binary odometer, you only have 0 to 1. Okay. Any questions so far? Okay. Did you miss anyone? So the next grouping is called a byte. A byte is 8 bits. It's also 2 nibbles. Do you follow? So the place values are as follows. 1, 2, 4, 8, 16. So ganito lang yan. The first is 1. The second is 2 times 1. The next is 2 times 2, 4. The next is 2 times 4, 8. You just multiply the preceding value with 2. Okay? Or exponent, an increasing exponent of 2's. No? So 16 is 8 times 2, 32 is 8 times 16, and 64 is 8. So you have to memorize this. No? All computing students will have to memorize the binary series. 128 to 56, 256, 512. 512 is 1024. After 1024, you have 2048. After 2048, you have 4196. 4196, you have 8192. I think I'm still correct. No? And then after 8192, you will have 16536. And then after 16536, you have 32768 or 767, depending where you start counting. If you start counting at 0, but the place value is 32768. Okay. Pagkatapos ng 32768, you have 65536. That's 64K. They follow? So you have to memorize this. Huh? Okay. MSB is 128, LSB is 1. Now, if you represent a byte, if you use a byte to represent positive numbers, the possible values are 0 to 255. If you use a byte to represent negative values, sometimes when you represent negative values, you spare the last bit, which means only 7 bits will be used. The spared bit will signify whether the value is negative or positive. A 1 means negative. So if you have a positive assigned number, only the 7 bits are used to store the magnitude or the quantity. The actual quantity will only be positive 127 to negative 128. Okay, only half. Why? Because we do not have 1 bit. The last bit is used for the sign. Okay. So we have to represent, remember, no, when we discuss about the early computers, how are numbers represented there? We say that the 701 represents numbers using fixed point. The other way is floating point. Okay. Now, basically, we use fixed point and floating point for fractional values, no? Ibig sabihin yung may decimal. But if there are no decimal, if we're talking about whole numbers, we talk about integers. Nowadays, in any language, when you say an integer is always 2 bytes. Right? C++, how large is an integer? In Python, how large is an integer? It's always 2 bytes. 16 bits. Okay? 2 bytes. For a signed integer, only 15 bits are used to store the value or the magnitude because the last bit is used to signify the sign. Okay? Okay? So, yeah. Sign. Hindi 2 bytes na tayo ngayon, no? Okay? Integers do not contain fractional parts. They're only whole numbers. Int. Ang tawag dyan sa C++, int. Now, in Python, there are no types. Okay? The type depends on the value that you assign. Okay? Consider the following numbers. What are the valid integers? 123 is valid. 0.987 is invalid. 0 is a valid integer. 0.0 is not. 79,903. 78,903 is a valid integer. 123.09 is an invalid integer. Okay. Now the sign bit indicates whether the number is negative or positive. No? The logic one indicates it's negative. No? The logic 0 indicates it's positive. Okay. Signed integers, 16-bit, no? Negative 32,768 to positive 32,767. That's 2 to the 15 because there are only 15 bits used. Okay. Now, for unsigned integers, no, the possible value is 65,536, 64K. To store larger integers, values should require more bits. Okay. Ang bilis ng oras. Here's a decimal comparison between decimal and binary integers. Okay. So, in decimal, when you say 13 base 10, it's actually 1 times 10 plus 3 times 1. You follow? 10 to the 0 is 1. In binary, now 13 is 110 equivalent. Why? Because it's 1 times 8. 2 to the third is 8. 1 times 8, okay, plus 1 times 2 times 0. 4 times 0, no? 2 squared is 4. 1 times 8 plus 4 times 0, that's 0, no? Okay, do you follow? 1 times 8 plus 2. 2 to the 1 is 2. Okay. Tama pa tayo? Sandali. This is 1 times 2. No, 4 pala, no? 1 times 8 plus 1 times 4. Okay. 1 times 2 to the 3. 2 squared is 4. So 1 times 8 plus 1 times 4 is 12. Plus 0 times 2 is still 12. Plus 1 times 2 is 13. Do you follow? So, in decimal, we say 1, 3 base 10. Okay. In binary, we say 1, 1, 0, 1 base 2. Do you follow? So, this is like going back to grade 5. No? I have a grade 5. No? My youngest is in grade 5. They're doing this. Okay. Now, the more difficult part is the fractional part. How do you represent fractions in binary and decimal? And now in decimal, when you say point, okay, 0.625, I'm sorry for this, no, kasi the worksheet is more 0.625. It's actually 6 divided by 10, diba? And then 2 divided by 100, and 5 divided by 1,000. So it's 6 times 10 to the negative 1 because 1 over 10 is 10 to the negative 1 plus 2 times 10 to the negative 2 because 1 over 100 is 10 to the negative 2, right? Any questions? Diba? So, the ascending series is in the denominator. Now, if you are on the integer part, the sending series is in the numerator. Beyond the decimal point, the ascending series is in the denominator. Okay, so 5 here in 625 means 5 times 10 to the negative 3. Do you follow? Do you follow? So in other words, we also say it's 6 divided by 10 plus 2 divided by 100 plus 5 divided by 1000. Okay? Paano yun sa binary? How is it in binary? In binary, 0.625 is 0.101. 101. In binary, it's 101. Okay? Why is it? Because we say 1 times 2 to the negative 1, which is 1/2. Okay? Plus 0 times 2 to the negative 2, which is 1/4. Plus 1 times 2 to the negative 3, which is 1/8. So it's still an ascending exponent in the denominator. The same thing, only the base is different. Okay? Okay? So 0.625 is 1 times 1/2, that's 0.5. Plus 0 times 1/4, 1/4 is 0.25. Plus 1/8 is 0.125. Remember, 1/8 is 0.125. Plus 0.5, that's still 0.625. Do you follow? No? So it's just a different language. The same way to count. Any questions so far? So you get used to this, no? When beyond fractional parts, the incrementing series is in the denominator. Before in the whole number part, the incrementing series is in the exponent of the numerator. Okay? Okay. There are two ways to represent fractions, no? Fixed point and floating point. Now, when we say fixed point, we assign a fixed location of the decimal point. Like in 26.5, the fixed location is between 6 and 5. Do you follow? Okay. Now, in the fixed point binary number, 26.5 is equal to 11010.1. 0.1, remember, is 1/2. So that's 0.5. The fixed location is in between 0 and 1. So in this case, we have a single digit fixed point number. If you want a double digit, you just move the location to the left. Okay? Okay? Now, take note. We will take a look at this later. No? How sure are we that 26.5 is equal to 11010.1? Because this first one is 1 times 2 to the 4th. The second one is 2 to the 3rd. So the 2 to the 4th is 16, 2 to the 3rd is 8. 0 is insignificant. This is 2, 2 to the 3rd, 2 squared. This is 2. So 0 times 2 squared plus 1 times 2. Okay, plus 0 times 1. Kasi 0 ito, no? And then this is a 0.5. So this is equivalent to 16 plus 8 plus 2 plus 0.5. That equals 26.5. Okay? Do you follow? So, for example, this is our number, no? And we are told that the decimal point is in the 4th location. For example, we have a binary number, and we are told that the binary number is here. Or the binary point. The binary point is here. What is the actual quantity? 10, we know 10 to be 2, right? Right away, we know 10 to be 2 because this is 2, this is 1. So 2 plus 0 is 2. Now here, what do we have here? The first is a 1/2, right? So we have 1/2, 2 to the negative 1. And the second is a 1/4, right? Because 2 to the negative 2. So this represents 2 plus 0.05 plus 0.25. 0.25 is a 1/4. So this is 2.75. Do you follow? Any questions so far?
Sir.
Okay, so
Sir.
simple math, no? Simple math, simple multiplication. For example, you're given a binary number of 0.10110. What is the actual quantity? We know that this one is 1/2. We know that this one is a 1/4, and this one is a 1/4. This is a 1/8. Okay, a 1/8 is 0.125. Okay, and this one is a 1/16. A 1/16 is 2 to the negative 4, no? 0.0625. We'll have that in Excel later, no? So this is equivalent to 0.6875. Okay. So in a fixed point number, this another terminology, no? The whole number part is called the range. So for example here, the range is 1, 0. This is the range. And the fractional part is called the accuracy. Okay. So it brings out the main drawback of a fixed point number. The fixed point number has limited accuracy. But why very limited? Because if you have two decimal places, you can only represent up to 1/4. O kasi 1/2 saka 1/4. Diba? 1/2 plus 1/4. That's very small, no? If you are using, if you are computing polynomials, for example, no, the accuracy is very limited if you have only two binary places. Any questions so far? No? So what's the alternative to fixed point representation? The alternative to fixed point representation is floating point numbers. No? Okay, floating point representation, which means that the decimal point or the binary point is not fixed. No, the location is not fixed. It can move to the left or to the right. Okay, so it has two parts. It's called the exponent, which is the power of 2, and the mantissa, which is the fractional value that is being represented. Do you follow? So to illustrate this, let us have an example. For example, how do you represent 12.5, okay, to floating point binary? Kung sa ano ito, if this is fixed point, this is easy. Diba? 12 is 1,100. Tama ba? 8 and 4. No? 1100.1. You can already know that because 12 is 1,8 and 1,4. Diba? So 1100.1. That's for floating fixed point. But for floating point, how do we do that? So, ganito na. We skip this part. No? We will discuss this with some. To convert a number to floating point, you continuously divide it by 2 until the integer part becomes a 0. You follow? Okay. So, for example, 12.5 divided by 2 is 6.25. Is this a 0? No, it's a 6. We continue dividing it. 6.25 divided by 2 is 3.125. It's not yet a 0, so we divide it again. 3.125 divided by 2 is 1.565. It's not a 0, we divide it again. It becomes 0.78125. We stop because this is now a 0. Okay. Now we count the number of divisions. 1, 2, 3, 4. 4 is our exponent. We follow? And our mantissa is 78125. No? So mantissa is the fractional part. 4 is the power of 2 that is going to be done, to be multiplied with the mantissa. So which means that, okay, the floating point representation is 78125 times 2 raised to the power of 4. Okay? 0.78125 times 2 raised to the power of 4. If you are going to use your calculator, that's exactly 12.5. Okay? You follow? Any questions so far? Which brings us to a more important point. How do we convert numbers? Kasi ito, we need to convert 0.78125 into a binary equivalent. Okay? So we still have about 45 minutes. We can do this quickly. And this is easy because the next part, which is converting positive numbers, is in one of the slides. There's also an example. We can also convert fixed point and floating point examples. No? Do you follow? Magko-convert tayo. We are going to convert not only positive integers, but also positive fractions in both fixed point and floating point. I hope by now you'll distinguish, no, the difference between a fixed point and floating point. Now, sa fixed point, there's a designated location of the decimal point or the binary point. In the floating point, the binary point will float depending on the number of times that we divide the number of two by power the number by two. Okay, so if you say 4 times, it will be moved 4 times. Okay, any questions so far? So we'll open a different slide, which is converting positive numbers. Do you know how to do this? There's a lot of this in YouTube. No? Everyone, marami ito sa YouTube, no? But not everything, okay, converts. The method that I'm going to show you is a method that will apply to both integers and fractions, okay? Kasi the method that you see in YouTube will have a method for converting integers and another for converting fractions, no? So yeah, it's cumbersome. Now, how do you convert an integer? Okay, to convert an integer, you divide the number by 2 until the quotient becomes 0. And each time you just remember the remainder, the mod. No? And then you reverse the remainders in a different order, no, opposite order. Can you have an example of this? Can you have an example? 53.625. Can we do that? 53.625. Okay. Shall we do that? Let me prepare my my cursor. I'll just see. I hope you can see now. Video. Let me set my light. You may not see my writing. Okay. Let's have an example. Let's convert a positive number from decimal to binary. Okay. I'll have to stop my. I'll have to create a new share. No? Okay. Let me see if I can. Yan ang makikita dito. What can you see? Okay. Let me arrange later. Okay. Can you see my writing pad, everyone?
Yes, sir.
Okay. So our example is 53. We'll do it this way. Okay. 53.625. We will convert this into binary. Okay. The thing is, we will convert the fraction and the integer separately. Okay, because we are going to use two different methods. For the integer, we do continuous division until 0. For the fraction, we will do continuous multiplication until 0. Do you follow? So first we have 53. 53. Okay, divided by 2. Okay, 53 divided by 2 is 26, right? 26, right? Okay. It's easy, no? 26 times 2 is 52. The remainder is 1. We'll write 1. The first remainder is 1. Okay? Do you follow? Now, what's our quotient? 26. I hope it's clear, no? 26 is not yet a 0, so we divide it by 2 again. 26 divided by 2 is how much? 13. 13 times 2 is 26. The remainder is 0. We write it here. Okay? Do you follow? Any questions so far? Okay. So, ano ito, no? Grade 5. Grade 5 arithmetic. Okay. Sometimes we can't even multiply 6.25 by 2. No? Okay. Because it's a grade 5. 13 divided by 2. 13 divided by 2 is 6. 6 times 2 is 12. We have a remainder of 1. 1. Now, 6 is still not a 0, right? Yan ang 0. So we continue divide 6. 6 divided by 2. You can see this in YouTube, no? 3. 3 times 2 is 6. We have a remainder of 0. So we write this again. 0. 0. And then 3 divided by 2. 2. 2 and 1. 1. 1 times 2 is 2. We have a remainder of 1. And then finally, we'll have 1 divided by 2. 1 divided by 2 is a 0. 0 times 2 is a 0. And then the remainder of 1. Okay? You follow? I hope you can see. I'm sorry, no? I didn't know. But you can see this part, right? Let's erase this. Let's go back. No? Okay. Can you see that part? I'm sorry, I wasn't looking. No? Okay. Click tayo, no? So 3 divided by 2 is 1 times 2. Remember 1. So this is, where is the 0? This is the 1. This is the 0. This is the 1. This is a 0. So this is a 1. Okay. Let's say yun yung 0. Okay. Tama ba tayo? 1 na lang. Okay. Anyway, 1 divided by 2 is a 0. Remember 1. Okay. Ito ko lang isulat. 1 divided by 2 is a 0. Remember 1. Okay. You follow? So our remainders are 1, 0, 1, 0, 1, 0, 1, 1. Do we reverse that? Going upwards. So 53 is, how much is 53? 1, 1, 0, 1, 0, 1. Is that correct? Okay. Can we double check? This is a 1, this is a 2, this is a 4, this is an 8, this is 16, this is 32. So we'll have 32 plus 16 will give us 48. We don't have an 8 because it's a 0, right? But we have a 4 because it's a 1. Plus 4 will have 52. Okay. We don't have a 2 because it's a 0, but we have a 1, so this is 3. Do you follow? Any questions so far? So to convert an integer, we continuously divide it by 2 and keep note of the remainder, and we reverse the remainder, no, until such time that the quotient is a 0. Pag 0 na, we stop. Okay. Any questions? I hope you can see my writing. No? I have a very limited space. Anyway, this is recorded. The problem is I don't have my eraser. I'm not used to doing this, so I get lost. I have an eraser. It's here. Okay. So now we will convert 0.625. Can I erase this? I will erase the blackboard. We now have 53. How do we convert 0.625? Okay. 0.625. We multiply it by 2. 0.625 times 2. 1.5 ba? Is that correct? 1.5. Right? Let me have my Excel. I have my Excel first to make sure. No? I have my Excel here. So it's okay. Yeah, point. The problem is I don't have a keyboard. Point 625. Okay. Times 2. So it's not used to typing my on the keyboard. Mali. Sorry, this is a 2. Was 2 times 25. 1.25 pala, no? I'm sorry, it's 1.25. Okay? Do you follow? Any questions so far, no? So ito, there it is, no? It's 1.25. Okay? So this is 1.25. We will remember the 1. There's a 1. Okay? So 0.25 is not yet a 0. So we have 0.25 times 2, which will give us 0.5. Okay? Una yung 1, no? So 0.5 is not yet, no, then we'll have a 0 because this is a 0. Okay? We follow? We'll remember the integer part. 125 nga, thank you. No? And then, so we'll have 0.5 times 2. Can we proceed now? 0.5 times 2 is, okay, 1.0. You follow? So now this is a 0. Okay? And this is a 1. So 1. And then we reverse it like that. Okay? The same way. You follow? So 0.625 is equal to 0.101. Is that correct? Because this is a 0.5. This is a 0.25. This is a 0.125. So we add this together, we will have 0.625, right? You follow? So 0.625 is equal to 0.101. So therefore, 53.625 is equal to 110101.101. Okay, this is our final answer. Okay. Any questions so far? That's fixed point. Fixed point. Let's go back to our floating point. Okay. Let me show you my floating point. Huwag na lang natin ito niyan, no? Because we will need this. No? Kasi yung floating point, example, no, not this. No? Can you see the PowerPoint if I do it that way? Ito. This one. Can you see that? Okay. Do you follow? Diba? In fixed point, what we have here is 53.625. We have a range of 110101. 110101. And our accuracy is 101. Okay. Now for floating point, can you see that? Okay. Our exponent is 4. Our mantisa is 0.78125. Okay. Can I erase this? Mahirap pag-erase, no? Difficult to erase. That's why, as much as possible, we'll just use Excel next time. Okay. I'm just doing this for you to understand the whole process, but next time I'm not going to do this again. Okay. Let me write the exponent first. Okay, and the mantisa is 78125. Okay. Can you now see the exponent? Do you follow? Okay. The exponent is just 100, right? Okay. Do you follow? The 71825, it's very large. You'd like to convert this? 78125 convert to ano? No, we will not do this. It's very difficult, no? We just Okay. Is there a way to convert this? 78125. Nandito yung decimal point, ang binary point, no? Yeah, there's a way to do that, no? Let me share again. Change my share. Basta alam natin 0.78125, no? It's in my notes anyway. Okay. Can you see my share now? Okay. You follow? Because we are going to introduce a new way, no? A new way to convert. You know that in Excel we have a formula called dec to bin, right? You want Excel? Okay, you follow? No? For example, we have 1024. We'll say equals dec to bin of this. Format na lang natin, no? Maybe it's a format. Ayaw talaga, no? We'll say 65. Okay, CC, no? 65. The problem with dec to bin is it only converts small values. Okay, 128. Yes, it converts, no? But when you put it a large value, ayaw na niya. Hindi na niya kaya. Okay, it doesn't convert anymore. So how do we do this in Excel? We will use a value called pick, mark, and subtract. No? A process. Now you can see this in YouTube. The problem is there's no process, no? That uses this with fractions. No? So pick, mark, and subtract. Okay. Any questions so far? Meron pa tayong 30 minutes, no? So kayang-kaya pa. Pick, mark, and subtract. No? So ganito yan. We lay out the binary series, integers and fractions in a table. Do you follow? We pick the value in the table that is immediately lower to the value to be converted, the maximum value next to the value to be converted. Once we pick that value, we mark it in the table as 1, after which we subtract the value from the original number, okay, and do it again until the value becomes 0. Okay. Mark the vacant squares of the table as 0 and join all the marks all together in normal order. Okay, let's have an example. 78125. Okay. Okay, convert 78125. 78125. So first, we lay out the binary series, including fractions. So we must reach a value in the binary series which is not greater than 78125. Okay, just a little smaller. The first value is 1, 2, 4. If you have a difficult time, you just multiply the no. Kulang ito, no? So 78125. Okay, what we'll do is just we multiply, no? Okay, it equals this times. Okay, and then we just copy this. Pwede bang ganyan? Ayaw eh. So we just copy this. Just copy this again several times. Kulang pa yan, no? Because we have 78125. Just trying to shorten this myself. Insert na lang tayo. Transfer this here. 88125. Okay. Are you following me? Can you see my, I hope you can see my worksheet, everyone. Okay. I am laying out the binary series. Kulang pa rin kasi because this is lesser, is still lesser than 78. Now, this is still lacking. Have to insert. But just a few more, no? Okay. Okay. Now, 32,768. The next is 65,536. Okay. So now, the next is bigger than, we cannot have, we stop them from there, no? We stop from there. Why? Because the next is already bigger than 78,125. Times 2 mo ito, 128 na eh. It's already 128. Okay. 132, I'm sorry, no? 132, which is already bigger. Do you follow? Do you follow? No? Okay. So, how do we pick, mark, and subtract? So this is, okay. First, we pick the nearest. Where is the nearest value which we can subtract from 78? Anyone?
65,000.
65,536. So we pick this. We mark this as 1. Okay? Because we picked it. And then we are going to subtract it from our current value. Okay? We just put some. Oh. The next value is 12589. Okay? 12,589. What is the next value we can subtract? Can we subtract 32,000? Anyone? No. Kasi mas malaki. Can we subtract 16,000? No. And Mr. Yap is correct. We will subtract 8192. So we will mark this as 1. Okay? So we will subtract 8192. And then we sum. You know how to sum. We have 4397. What can we subtract from 4397? We have 4096. So we mark this 4096 negative. Subtract. Okay. 301. What can we subtract from 301? We cannot subtract 2048. We cannot subtract 1024. We cannot subtract 512. We can subtract 256, right? Yes, that's correct. 256. So we subtract 256. Okay. We have 45. So what can we subtract from 45? We have 32. We cannot subtract 128 and 64. So we have negative 32. Subtract again. We have 13. What can we subtract from 13? 8. Negative 8. Actually, alam na natin. It's clear at this point, right? 5. What can we subtract from 5? 4. So this, we'll just continue here. 5 minus 4. Okay, like 1. And finally, we can subtract 1. Okay. So now, the remaining squares, we fill up with zeros. Okay. So this is the equivalent of 78125. How can we check? How can we check? We'll multiply this with that one. Diba? Am I correct? Equals this times that. Okay? Kupihin natin. Copy this until there. Okay, and then what we'll do is we will auto sum. We'll auto sum this. Okay, so this is 78125. Do you follow? So very easy, no? Let's have another example. Okay, we still have time anyway, no? 15 minutes. It's long time for an example. I have an example, a worksheet example there in our web page anyway. Let us convert 53 1 156.5245. Okay? You follow? Okay? Kaya natin ito, na? So, you have 1 equals this times 2. Just copy this. 128. Hanggang 128. 128 is enough. Ay, sorry na. Let's do undo. 128 is enough because the next thing is bigger than 156. So what we'll have here? We'll have here as 0.5, right? That's 1/2. And then this one we'll just divide by 2 again. Okay? Do you follow? And then we'll copy this. Now, from now on, no, we will only count 1, 1, 2, 3, 4, 5, 6. Okay? Bakit ganon? Yes. Now, every time we convert until we reach 0 or we reach the 6th binary place. Okay? Kasi the 7th binary place is a very small number. Do you follow? Do you follow? Okay. Okay.
Yes, sir.
Okay. Kasi hindi tayo, there are numbers that which cannot have exact equivalence. And sometimes you can go on the whole night na, and then you will not get an exact equivalent. So we stop at the 4th or the 6th binary place. Okay. We'll move this. So we can have space. We will improve this worksheet later, no? There's an example in our web page. Anyway, no? Okay, what's the first we can subtract? Anyone? 1 to 8. Let's do this fast. Kasi 10 minutes lang, no? Dali lang ito, no? So 28. What can we subtract? 16. Minus 16. 12.5. What can we subtract? We can subtract 8. Okay. Then 4. We can subtract 4. Okay. You follow? Now we have 5.5. Can we subtract 2 from 0.5? Obviously not. No? Can we subtract 1 from 0.5? Also, we cannot. No? Can we subtract 0.5 from 0.545? Yes. Okay, so therefore we'll do that here. So we'll say fixed point ito, no? By the way, this is fixed point, no? Minus 0.5. Hindi pa ito floating, but floating point we don't have a problem because we don't convert fractions. Okay? Walang conversion ng fraction sa floating point. Anyone? Okay. 0.245. So now we will mark this. 0.0245. Can we subtract this? No, this is bigger. Can we subtract this? No, this is bigger. Can we subtract this? This is still bigger. Can we subtract this? No, this is bigger. Can we subtract this? Yes. Okay. So we'll just copy this. Then paste that. No? We'll turn this into a negative. Okay. 0.008. So we have subtracted this. Now this is the 6th decimal place or a binary place. We don't go further. This is a very small value already. Okay. Do you follow? So we will, we will put in the blank zeros. Okay. And then we will concat. Okay. Equals concat. Hanggang dito, no? And then we'll put in a binary point. Okay. Ayaw niya pumayag. Ayaw niya. Ayaw niya. So we'll just concat it here. Okay. And then we'll put a binary point. Okay, do you follow? And then we'll concat another one. Starting from this. Okay. So 156.5.542.45 is equivalent to this. This is the range and this is the accuracy. Do you follow? Do you get my point? Now, in our website, I have an example, no? 53.625 conversion. No? I think we have done this. No? Okay. Worksheets. This is what? Fixed point conversion. Converting positive numbers. Do I have that? Nawala. Pero anyway, nandito siya. So, yan, no? They follow. This is the fixed point of 53.625. They follow. We have done this manually, no? Anyway. And the floating point. So 53, we divide by 2. This is 26. 26 divided by 2. And then 13 until we reach this. So how many times did you have this? 1, 2, 3, 4, 5, 6. So our exponent is 110. Do you follow? 110. And our problem is 837. This long number, we just, we just abbreviated it to 83789. Okay. We converted this into, using pick, mark, add, subtract. We don't have problems with fractions, no? Okay, do you follow? So this is our mantisa. Okay, and this is our exponent. This is the floating point representation of the number 53.625. Okay, this is the floating point representation. This is the fixed point representation. So now I hope it's clear to you, the difference between floating point and fixed point representation. In floating point, the decimal point will float depending on the number of times that you divide the number by 2. Diba? Because there's an assumed decimal point before the 8 right here. Okay? It shows that the floating point representation can represent more accurate values, very small numbers. It can represent very small numbers because it can change the position of the decimal or the binary point depending on the value that's going to be represented. Okay, so remember the PDP1 is floating point, the 701 IBM 701 is fixed point. Okay, do you follow? No, that's why floating point computers used to be very expensive because the conversion is different, is difficult and different. Okay, any questions so far? Next meeting we will have more examples because this will be the main component of your next formative test. There's a lot of material in YouTube. Okay. So if you have no questions, okay. See you next meeting. I will answer the test next meeting. Okay. Did I miss anyone? Okay. Who's a newcomer? No one. Casiano. Sevilla. Okay. Okay. So thanks for coming. Okay. We're just about to close at 3 o'clock. We have 5 minutes spare, but we don't have to, introduce a new topic. We can finish an example even, okay? Thank you very much for coming, everyone.
Thank you, sir.
I'll save this and
Thank you, sir.
post it.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.